Hello, everybody. Welcome back to part two, where we take everything we learned and we scale it up to multi-qubit circuits. So in this section, I will break things down in a similar way as before. So first, I will work through some notation for talking about systems of 2 qubits. Then I will introduce you to 2-qubit quantum gates. I will then take a while and go into an example of constructing a 2-qubit state called the Bell state, and I will use this as a demonstration for this phenomenon of quantum entanglement. Then I will generalize even further how you can think about an n-qubit circuit. And then just like before, we'll take all of that mathematical jargon and information and try to view it through the lens of making a quantum circuit a computer for us. So when we're talking about a 2-qubit system, we will first think about what if we just want to describe two particles that have some property that we want to model, and these particles aren't interacting with each other in any way. They're just completely independent. Well, we could model each particle property individually as a qubit. And so if we have a 2-qubit system like this, we can just clone the definition of a single qubit and change the vector entries so that they're mathematically distinct, and we have no problems there. Additionally, one aside. So I spent some time in the first part really getting into the technicalities of observables and making measurements. And we could have variable observable matrices. For the remainder of this presentation, we are only working with poly-Z matrices. This is the default in the literature, and you will see that it makes the mathematics much easier as we scale up. So what this means is for each of our qubits, we can take a measurement, and each one individually will collapse down to either the 0 ket or the 1 ket. I want to introduce some ket notation to talk about the aggregate measurements of the system. So what happens if our first qubit became a collapse down to a 0 ket, and our second qubit also collapsed down to the 0 ket? Well, we can describe this aggregate state as just the 0, 0 ket. And likewise, we have these 2-digit ket notations. So the first digit will always describe the outcome of the first qubit measurement, and the second digit will always describe the outcome of the second qubit measurement. What this leads us to is a way to describe a 2-qubit system in a Z basis still. So we can represent this aggregate quantum state of 2 qubits using these 2-digit kets that we've just introduced and their corresponding probability amplitudes. So for psi here, which is now representing 2 qubits, we can treat it as this following sum, where each probability amplitude, for example, A00, will be scaling our ket of 0, 0, and so on. And what's very convenient about this notation is if we're taking measurements, again, with the poly-Z observable, then the probability that we measure some ij ket is equal to the aij, so that probability amplitude modulus squared. And you can see here I've shortened the notation for measurement probabilities because we just are assuming the poly-Z observable everywhere. Now, these kets also form a basis of a 4-dimensional space in a fairly straightforward way. We just, for each ket, we have a 1 in certain entry and 0 everywhere else in this descending pattern. So another way that we can write our quantum state, if we start with a qubit, a two-qubit system in the following z-basis form, is just as this vector with each entry being a probability amplitude. And what we require in order for this to be a legitimate qubit state is that the inner product of psi with itself is equal to 1. Now, this is where things start to get a little interesting, because this definition, as we have it here, is very similar to the definition of a single qubit system, with the exception that we are just scaling up the number of probability amplitudes that we can hold. But we still have this requirement about the inner product. And we will see that there aren't as many differences between a multi-qubit system and a single qubit system as one may think. I want to dive a little bit more deeply into how we would determine these probability amplitudes for this aggregate quantum state. So we're still in the context that these particles are not interacting with one another. And so we have qubits with the probability amplitudes here of alpha and beta for our first qubit, and gamma and omega for our second qubit. And if we want to write psi, the aggregate quantum state, in a vector form, we have a formula for doing this. So psi is equal to the tensor product of our first qubit with our second qubit. And so the entries will be defined as you see here. Now, just to give an update or a brief review, a tensor product is defined as follows. If we have some vector v in an n-dimensional space and a vector w in an m-dimensional space, then the tensor product of v and w is of dimension n times m, and each entry of their tensor product is a product between an entry of v and an entry of w. And this is defined in such a way that all possible combinations of products where one factor is an entry in v and one factor is an entry in w are accounted for. So I want to give a concrete example to this. So let's say we have two qubits that are each the zero ket, which we should be familiar with what these look like as vectors by now. If we look at the aggregate state psi as the tensor product between these two vectors, then it evaluates as follows. So we take the top entry here, multiply it by the top entry here for this entry. In this entry, we take the top entry here and multiply it by the bottom entry here. In this entry, we take the bottom entry here and multiply it by the top entry here. And finally, for this entry here, it's just the bottom times the bottom. And if we evaluate this, we see that we get a 1 in the first entry and 0 everywhere else. And this is just equal to our 0, 0 ket. So from this example, we can see that if we start with a qubit system where one qubit is the 0 ket, the other qubit is the 0 ket, then the aggregate state is the 0, 0 ket. So this should not be all too surprising. But let's do a sanity check in Pennylane just to make sure that the simulator is doing what we expect. So here is the circuit. The novelty here is that instead of having one wire, we now have two wires because this is a 2-qubit circuit. And this is otherwise identical to our very, very first example. And so when we print out the state, we see that we get a 4-entry vector. We have a 1 plus 0j, so just 1 in our first entry, and 0 everywhere else. So everything is working as expected. Pennylane is behaving in a in a sane way, and our mathematics is correct. Okay, now that we have a 2-qubit system, we would like to apply a 2-qubit quantum gate to that system. And in order to apply a 2-qubit gate, we require now a 4x4 unitary matrix. And just like in the single-qubit case, this gate will act as a unitary transform. The only difference is that we are scaling up the dimensions. So now it transforms this 4-dimensional state vector into a new 4-dimensional state vector. The formula here is identical to the single-qubit case. To introduce you to a 2-qubit gate, I want to give you the C0 gate. This is a very commonly used gate in circuit diagrams and in the literature. The C0 matrix is just a matrix defined here on the left side. What this matrix does, if you apply it to a 4-entry vector, is it will just swap the values in the 3rd and 4th entries. And if you see this symbol in a circuit diagram, so this would be the wire for the first qubit and the wire for the second qubit, then this symbol represents a C0 matrix transformation on those 2 qubits. A question might come up for you. What happens if we just want to apply a single qubit gate in a 2-qubit system? It's not clear how we would do this in a mathematically sound way, because we couldn't multiply we could not multiply a 4-dimensional state vector by a 2x2 unitary matrix. That's not mathematically sound. So what we do in the case of a single qubit gate is we view it as the matrix tensor product between our intended gate matrix and the identity matrix. So we'll work through an example of how to do this conversion. So to do this, I'm going to introduce another very commonly used gate called the Hadamard gate. This gate, or this matrix written as H, is just defined as follows here. We can see that if we apply our Hadamard gate to a single qubit system, alpha beta, this is how alpha and beta are modified, or how the entries of the qubits are modified. And typically, we represent it with this box with an H in the middle for the Hadamard gate. And now what I want to do is convert this 2x2 matrix into a 4x4 matrix, which will apply the Hadamard gate transformation to only the first qubit and do this all in a mathematically sound way. So to do this, we will calculate this H prime, which is the tensor product between our Hadamard matrix H and the identity matrix of the 2x2 identity matrix. And I haven't formally defined how we work with matrix tensor products in terms of the indexing of different entries. However, a sort of intuitive way to think about it is that we take each entry of our Hadamard matrix and we multiply it, so to say, by the entire identity matrix. And so in the end, what we're left with is this 4x4 matrix. And I leave it as an exercise to you to show that this tensor product, so this matrix here, is a unitary matrix. So it is obeying all of our rules on what a quantum gate can be. And something a little more involved is to show that if you are applying a Hadamard gate to only the first qubit in a 2-qubit system, that you can use this trick of the matrix tensor product conversion, and this will have no effect on the probability amplitudes of the second qubit, provided that these qubits are isolated, and you can write the aggregate state as a tensor product. So I want to now construct the Bell state, because I think that this will help show how a lot of these concepts are very interesting, and it will show us some very interesting things about quantum physics, and also by extension quantum computing. So my goal is to build a circuit which constructs the Bell state. The circuit, the state that I want to construct is defined as follows. So it's the 0-0 ket, where we then apply a Hadamard gate onto our first qubit, and then we apply a C0 gate onto our quantum state. And I will make the claim that in Pennylane, when we do this and we view the state, we will get the following vector in Z-basis form. So we will have a 1 over root 2 for our 0-0 ket. We will have probability amplitudes of 0 for our 0-1 ket, 0 for our 1-0 ket, and a probability amplitude of 1 over root 2 for the 1-1 ket. I leave it as an exercise to you to prove that this expression in the top equation evaluates to this expression in the bottom equation. And I also want to ask a question of you of what do you expect us to observe when we measure the Bell state? Okay, so first of all, I'm going to just describe our Bell state constructor. So I've just implemented the circuit that I have previously described on the slides in Pennylane. And now we can see that our circuit diagrams are starting to get a little bit interesting. So here we can see how this first qubit is passing through this H, and then it's passing through, then both qubits are passing through the C0 gate. And now we're just peeking at what state we get. And if we look at it, we can see that, if you remember that 1 over the square root of 2 is equal to 0.707, et cetera, that we get the Bell state that we want. Okay, and now what I'm going to do is I'm going to observe the qubits. I'll take 10 samples, and when we're looking at this, let me go down here. So here is this, here is our circuit after we've made some measurements. So this top row here represents the measured eigenvalues of our first qubit, and this bottom row are the measured eigenvalues of our second qubit. And you might notice a pattern here, which is that whenever we see a -1 on the top row, we have a -1 in the corresponding entry in the bottom row. Likewise, if we see a 1 in the top row, it's always a 1 in the bottom row. But maybe this was just a fluke, coincidence. So what happens if we run the circuit again? Okay, so same pattern, as you can see. Okay, same pattern. Same pattern. Okay. What's a little strange about this is that it seems like if we just looked at this top row and what we measured, then we'd be able to know exactly what we will measure for our second qubit. And if we crunch the numbers and apply and look at the measurement probabilities, we see that half of the time we should observe the 0-0 ket state. So that would be when we see a 1 in the top row and a 1 in the bottom row. And half of the time we should see the 1-1 ket state. So we'd see a -1 in the top row and a -1 in the bottom row. And What's interesting about this is that, we can predict the outcome of our second measurement with perfect accuracy, just looking at our first measurement. And what's interesting about this is, let's say that we create a Bell state, and I give you one of the particles that is used to create this Bell state, and you go very, very far away. You go so far away that there's no way to communicate with you very quickly. And you and I both agree to measure our qubits at the exact same time, and such that even if we could communicate at the speed of light, there's no way that you could know the outcome of my measurement before you make your measurement. What will happen, or what the math will tell us, is that we will always make the same measurement. And this phenomenon is known as entanglement. And I think this is just something that's very, very compelling about quantum physics. It's not very clear why these particles are always giving us the same observations, or that they are always measuring to the same values. However, the mathematics says that this is exactly what should happen. It's not clear if they're communicating with each other. Perhaps they agree beforehand how they will collapse down. We really don't know why this is happening. The formal definition of entanglement is that we have some sort of mixing of probability amplitudes across the qubits. What this would mean is that a qubit state is entangled if you cannot factor the aggregate state into a tensor product. So if you remember, our initial qubit state is factorable. The 0-0 ket is the tensor product between the 0 ket and the 0 ket. However, for the Bell state, there's really no sound description for these qubits in isolation. There's no way to solve the system of equations required such that you have a valid description, or you have something valid to place where there are these question marks. And so this phenomenon of quantum entanglement is very, very intriguing. And just as a small aside, the 2022 Nobel Prize for Physics was awarded for some experimental demonstrations, very rigorous experimental demonstrations of this phenomenon of quantum entanglement. So this is really cutting edge stuff that people are really still trying to learn quite a lot about. So for systems of more than 2 qubits, we can take the lessons that we've learned so far and use them to generalize even further. So if you recall, if we had 2 qubits, we had a vector in a 2 to the 2 complex dimensional space. But as we grow and we have now an arbitrary n number of qubits, we have a vector in a 2 to the n complex dimensional space. So if n equals 3, and we want to deal with 3 qubits, then we can write the state psi as the sum of all of these ijk kets, where ij or k are either a 0 or a 1, and they're each scaled by their corresponding probability amplitude. Again, we require that the inner product of the system of the psi ket with itself is equal to 1. And again, the probability that when we make measurements of this state and it collapses down to the ijk ket is equal to the modulus of aijk squared. Likewise, if we want to apply a unitary, or if we want to apply a quantum gate to a system of many qubits, we just need to specify some unitary matrix of size 2 to the n by 2 to the n. And everything will behave as before. The gate is just a unitary transform of our qubit state. And again, if we have a smaller quantum gate that is really only used for a subset of these qubits, then we can use the same tensor product multiplication rule, where we take the tensor product of our initial unitary matrix by the identity matrix to scale things up to the appropriate degree. There's also some index shuffling that you need to account for, but I want to just make this general idea clear that there's a mathematically sound way that we can think about quantum gates operating on only a subset of qubits in a larger system. Similarly, if we have a system of more than 2 qubits, each measurement is performed on each qubit separately. And there are some practical cases where you might only want to measure some of the qubits in a system. And then sometimes, depending on the outcome or not, you may apply further gates to the unmeasured qubits. This is all mathematically very well defined. However, the mathematics here gets a bit treacherous, and it's beyond the scope of this presentation. And lastly, once we take these measurements, we have essentially broken entanglement. Our qubits are again in isolation, and we can state the qubit state again as a tensor product. Okay, you know the drill by now. We've presented all of this technical information, and I want to now think about what this means for us as computer scientists and researchers when we want to get these circuits to work for us as computers. So a quantum circuit can really be thought of as a series of unitary transformations that are applied to an initial qubit state. Now, a series of unitary transformations can itself be simplified to just be a single unitary transform. And if we want to think about the quantum circuit as just one giant unitary transform, we will label the transform described as this matrix U. So if we have an initial state psi ket, all that a quantum circuit is doing, namely all of the gates, is just applying some unitary transformation U to give us a new quantum state psi prime. And then by repeatedly running and measuring this quantum circuit, we can get some estimates of what the probability amplitudes of psi prime are. As we remember from our exploration of the single qubit system, it takes quite a while to get accurate estimates of this. Yeah, it's generally very challenging to know what the exact probability amplitudes are. And it becomes challenging to measure them. And again, the measurement probabilities are related to the probability amplitudes. 1 second. Okay. Now let's think about what this means in terms of the scale of the computations that we can perform. So an n-qubit system is a unit vector in a 2 to the n complex dimensional space. U, our unitary transform, is a 2 to the n by 2 to the n size matrix. We can construct U through a product of unitary gates. And the really critical thing to emphasize is that we never have to hold this U in classical memory. When we are constructing this quantum circuit and applying these transforms to physical qubits, you can kind of think of U as being stored in Mother Nature's computer, so to say. Nature is taking care of all of these calculations for us. And this is something that we can use to our advantage. with the examples that we were working with, we were able to simulate them perfectly with just a classical machine. But you can imagine that as you scale up this n, the number of qubits that you're working with, because we have an exponential growth in terms of all of the entries of these matrices and vectors that we need to keep track of, this becomes rapidly intractable on a classical machine. Another small point that I want to make is that just because the circuit itself is a unitary transform, that doesn't mean that quantum computers are limited to just simulating linear functions. And the reason for this is that if we have a linear transform in a high dimensional space, we can project it down into a lower dimensional space and it will become a nonlinear function. As an example for this, remember that we were able to use a quantum circuit to model a cosine back in the single qubit section. You still may be a little skeptical about the power of this computing model. You may think, well, it's still just a unitary transformation at the end of the day. So what can you do with this? And my reply to that is that unitary transformations are fairly powerful. One very clear example is that you can describe the one-dimensional discrete Fourier transform as a unitary transformation. And so just so we are familiar, the discrete Fourier transform is defined as follows. And again, I leave it as an exercise to you to show that this transform is actually a unitary transform, but you can take my word for it, it is. And in fact, this is so popular that if you perform a discrete Fourier transform on a quantum computer, there's a special name for it. It's referred to as the QFT, and the inverse is QFT inverse. The QFT, or rather the QFT inverse, is very critical in some well-known quantum algorithms. So it plays a crucial role in an algorithm called Shor's algorithm, which can factor an integer very, very quickly. So here I have a quantum circuit diagram, which is the critical subroutine in Shor's algorithm. In Shor's algorithm, there are some classical pre- and post-processing. However, the really intractable, the classically intractable component is covered by this circuit here. So I won't go into all of the details here because this is a very complicated quantum circuit. However, by now, some things should look very familiar to you. You can see that we're starting with some initial qubit state here on the left. We have these H's, which are Hadamard transforms. These U's are a little bit more complicated, and then we can see that we are applying the inverse QFT to a subset of qubits and then taking their measurements. And I won't go into all of the details now because it's extremely complicated, but this is needed to factor an integer very, very quickly. To dive a little bit deeper into how much quicker this works, the best known classical way to factor an integer is with the so-called general field sieve method. In this O notation here, n is just the integer itself, and this is the time it will take with big O notation to factor it. For Shor's algorithm, it's a little bit challenging to compare the complexity directly because there's some classical components and some quantum components, and so it's hard to make a direct comparison of speed. However, what people usually do is say they compare the number of quantum gates that are used as sort of a proxy for the speed. And so we can see based on this, the number of quantum gates is significantly lower than the number of classical computations that you would have to perform with the field seed method. And then there's also some classical pre and post processing, which doesn't contribute all too much to the final speed. And so on the right here, we have a graph of the number of operations in red for the general field seed method and the number of quantum gates in blue for Shor's algorithm. And so you can see that the number of operations grows far, far faster as the number of digits of our number grows in the field seed method than with Shor's algorithm. So all of this to say that Shor's algorithm is significantly more powerful and effective than the general field seed method. And even now you might think, okay, who cares about factoring integers rapidly? This seems like kind of a nerdy subtopic. This has no real world applications. However, this is actually incredibly pertinent to modern cryptography because Shor's algorithm breaks the security of many public key cryptography schemes. So some well-known ones are RSA and also the finite field Diffie-Hellman key exchange. So the way that these protocols work roughly is that their security is given by a proof by reduction to some sort of generally hard math problem. And in the case of these protocols, they rely on the fact that factoring an incredibly large integer should take a lot of time on a classical machine. However, Shor's algorithm bypasses all of this because we can just factor an integer relatively quickly. And this compromises these cryptographic protocols. And so an active field right now is post-quantum cryptography, which is this quest to come up with protocols that are both robust against quantum computing attacks and also classical attacks as well. So this is an entire field of study unto itself. Okay. I hope by now you understand the mathematics behind quantum circuits, and you have some appreciation for how powerful these circuits can be, and also you have some applications in mind for what you can use these for. And so now I want to close things out with an overview on the area of research that I'm looking into. And so this is quantum machine learning. I will give, I won't go as deeply into the details as in these previous two parts. In part, it's building on what we've already done and it's more complicated. Additionally, this is really an active area of research. And so there are still a lot of unknowns about what works and what doesn't work. For that, let me take a drink of water. Okay. So the natural place to start with quantum machine learning is to think about how we can treat our quantum circuit as a sort of stand-in neural network. And to start thinking about things, we want to consider the quantum circuit as just a function which takes a series of tunable parameters, here just theta, and we can think of our unitary matrix at U as as being dependent on these tunable parameters that we can change around in order to alter the behavior of U and therefore the quantum circuit. So if we split our tunable parameters theta into two subsets, some theta which we associate with input data and some data which we associate with weights, like you might see in a neural network, then we can begin to create a circuit which starts to resemble a neural network. So we are passing in some data as input, some data as weights. These get combined into some unitary transform U of theta, and then we will apply U of theta to some initial qubit state. This might as well just be the default state of an all zero ket state, and then we can take some measurements of our circuit. A common architecture pattern that you can see in some research papers today is the following. So what they do is they will take some classical data and they will treat these as the theta for the input. And then what they will do is something called angle encoding the data. And what this means is that they will start with a default qubit state with no entanglement, and they will take two pieces of classical data and use these to move the first qubit around to some point on the Bloch sphere. And then for the next two pieces of classical data, they will parameterize where the qubit moves on the second Bloch sphere, or where the second qubit goes on its own respective Bloch sphere, and so on until we encoded everything. And then we have some next section of the quantum circuit, which is parameterized by these thetas, which represent the weights. And in this section, we are generally entangling the qubits in some way, and we are also performing transformations that are parameterized by some tunable weights. And then finally, we are measuring a subset of these qubits for further processing. And this process can also be referred to as decoding. When we are using a quantum circuit for QML, we don't have to replace an entire classical neural network with a quantum circuit. And in fact, what the ethos of Pennylane is to do research into hybrid quantum machine learning. And in this paradigm, what we're doing is we aren't trying to completely replace a classical neural architecture with a quantum circuit. Instead, what we want to do is replace one or several layers in a classical neural architecture with a quantum layer. And the idea behind this is that hybrid architectures will just allow the best of both worlds. We will have some classical layers that can do things that classical computations are very, very good at. And then we can perform some sort of crucial, intractable calculations on our quantum layers to make a stronger network. A very, very basic example of such a hybrid architecture is from this paper by O et al. I believe that this was published in 2019. But this is the really basic, like, sort of hello world example of where this could go. So in this paper, what they tried to do was create a hybrid architecture that was just trying to classify the MNIST data set, so digit classification. And what they did was they passed the input images, these grayscale images, first into a quantum convolutional layer. And so here is a diagram just from their paper where they describe the architecture of this quantum convolution. So you can see in this layer here, they're actually doing the angle encoding as I described in the diagram previously. And then this section of the quantum circuit is actually a parameterized circuit. And then finally, they are measuring just one of the qubits as an output. And they want this to be analogous to a classical convolution that you would use in a network like this. What they were able to show is that if they had this, what they refer to as the QCNN, so this has a first layer with these quantum convolutions as I've described, and then it will pass on to classical convolutional layers and then an MLP for the final classifications. If they compare this with a CNN of comparable size, they get comparable performance in terms of the test set accuracy and the test set loss. And both of them are doing better than just a fully connected MLP for this classification, but that's no surprise. This is more of just a control. And so, not quite done. I want to say a few more things about this paper. So this is a very, very basic example, but I chose this to illustrate a few things. I think the takeaway from this paper is just that it is feasible to use hybrid machine learning and that you can integrate quantum layers. It leaves a lot of questions open of, could you use a hybrid architecture to make things better and perform better than a classical network? And how far can you take this? I also selected this paper because there were not all too many papers out there about QML. And so you can think if this is the state of the art in this direction, then there's quite a lot that we can still figure out about this technology. So this, we're getting near the end of the presentation. I want to just say a few things just about quantum computing in general, just a few things that didn't have a good place to fit in the presentation beforehand. So if you recall at the beginning, I said that we were just going to focus on gate-based quantum computing. We've learned quite a lot about quantum circuits, but there are other quantum computing paradigms out there. One such paradigm is the adiabatic quantum computing paradigm. And so this feels like a very different realm entirely. So what an adiabatic quantum computer can do is solve a binary vector optimization problem. So what this is I give the quantum computer some matrix Q, and then the computer will return an X with that is just a vector of length n with entries 0 and 1. And what it will do is return an X that minimizes, that will produce the minimum value here across all possible X's with entries 0 and 1. And this is the tip of the iceberg with adiabatic quantum computing, but this is the general idea for what this type of computing can accomplish. For adiabatic quantum computing, there is a widely known and commercially available service where you can actually purchase a subscription for this and send it your binary vector optimization problem. So it's this private company, D-Wave. Their entire model is we have these quantum computers called quantum annealers, and you send us your problem and we will send you back what our quantum computer calculated. And in terms of gate-based quantum computers, last I looked, I think IBM has the state-of-the-art, but in general, the adiabatic quantum computing, I'd say, is farther along technologically than the gate-based quantum computing. There are quantum computers in existence, but I don't think they are quite so powerful. I don't know, Vlad, if you have any comments on the state of these two technologies, or if you think, or if you can say how the gate-based quantum computing is compared to the adiabatic quantum computing.
Like the D-Wave is more advanced in terms of the number of qubits, but also the connectivity between them. And the problem sizes that can be solved. The gate-based model is still in its infancy, and only the smallest problem in terms of the number of layers can be solved. Most of the machines are not available to the public. For instance, Google, even they do not provide any kind of external access to their machines. IBM do, right, but to a little bit older models with 27 qubits over 16 qubits.
Okay.
Right. So,
yeah. Okay. Thank you. What Vlad said leads very well into one of my favorite XKCD cartoons, which is that these quantum computers are huge engineering challenges. And so in this whole presentation, we were talking a lot about the mathematics behind quantum computing and what we can do in an ideal world. However, mathematics is not the same as physics, as this cartoon demonstrates. So in mathematics, we don't have to worry about physical implementations of things. We don't have to worry about things like phenomenon like quantum noise, for example. You have to keep these quantum devices generally at very, very cold temperatures and extremely isolated, because you can think we're measuring these quantum properties. And so if we have any interaction with the outside world, we can just spoil our calculations very, very easily. So what I want to say with this is just take everything that I've said here, and if you think about what might be possible with quantum computing, add a grain of salt there, because with everything that I've said in this presentation, every line about what a quantum gate can do, there comes 1,000 caveats with the physical implementation. But people are dedicating a lot of time to working on this. Another piece of information that I'd like to share is, if you hear people talking about quantum computing, you will hear them say that we are in the NISQ era. And so NISQ stands for Noisy Intermediate Scale Quantum Computing. And I think that this name is a bit, it leads you to think that we will be out of the NISQ era. And a lot of times when we discuss it, we're given graphs like this, where we say, well, today we're in the NISQ era. We have quantum computers, but there are some challenges still. But in 5 years, these are going to be amazing devices. And so the number of qubits that we can model will be increasing exponentially. It will be far more fault tolerant. And I would just like to say, I'm not a quantum computing engineer. I am not on the ground when it comes to the actual challenges involved in scaling these things up and making them more resistant. So it's hard for me to fully believe in these graphs that are just posted on the internet. However, I do think it's pretty impressive how far this technology has already come along. And given the amount of time and money and very, very smart people who are dedicating themselves to these problems, I am cautiously optimistic that something like this could be the reality soon. I hope that you've enjoyed this presentation and you get the sense that there's still quite a lot to be discovered and figured out about quantum computing. It's something that I'm really enjoying about my thesis research here with Vlad and also with Eddie Ilg. So if you were also inspired by this presentation and would be interested in a thesis, the 4D and quantum vision group might be for you. So there are potential thesis topics in quantum computer vision and graphics. And you can follow the link on this slide. These slides will be posted soon, or this presentation will be posted soon. And the group was established a few years ago by our very own Vladislav Bolyanek. And yeah, if you're interested in an internship or a thesis, please reach out. Additionally, I didn't make this presentation just completely out of my own head. I had some resources along the way to help me. So if you want some introduction to the simulator and you want more of a hands-on look at quantum computing, I do recommend the Pennylane documentation. I think the best way to learn about this stuff is by playing around with the simulators. And if you want more of a tough, comprehensive textbook that will give you all of the math, I would recommend Quantum Computation and Quantum Information. The order that they introduce things is slightly different than what I did. However, it's all there, and it's a really excellent textbook for this kind of information. Thank you for your attention.
A very nice, insightful presentation. We have time for questions. So if you have a question, please, also online, let's keep them live.
Just the question, you represented some other algorithms, but it might be, maybe you have nothing to do with QFT. Maybe you did a bit nothing.
So I showed...
Yeah, you showed the short.
Yeah. Yes.
I was wondering that the encoding of the qubits with the quantum machine learning, is it similar to the QFT? Because in QFT, as I understood it, right, is a bit like also angling it, but maybe you have nothing to do with QFT, then it doesn't matter.
Okay. I see what you mean. I would say the key difference is that the QFT is a set matrix where the entries for this matrix are just given by the formula here. So these e to the negative I blah 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 blah. So there's no point in which you might take some classical data and change the content of the QFT matrix because of this. It will just always be the same values. For encoding, you're encoding using some sort of tunable parameter. So I would say that in that respect, it's different. I think you wouldn't be able to, well, I mean, what you could do is take the QFT, or sorry, you could take some data and then take the QFT of it, and you can argue that you have encoded whatever data you initially had into a frequency space, as opposed to the alternate, the just physical space that you started. But yeah, I'd say that would be the comparison between these two.
Maybe something to add is that in QML, often we're interested in encoding classical data in quantum states, whereas QFT operates already on the quantum data. So the classical data first has to be encoded as quantum states before, let's say, applying QFT or applying the set of other gates, but not in the QML area, but in general area of quantum algorithms. QFT is often the first step in many algorithms. But this is something different. Any other questions? Yes.
Is there any known computational complexity related to the QMT? Because I'm thinking about computational complexity in the case of fast free transform, which is known as analog measures. Is there any result related to this? Or also, can this be generalized to higher dimensional acts here?
Okay. So in terms of the computational complexity, the first thing I'd say is that this whole quantum circuit is going to happen in the blink of an eye. It's going to happen very, very quickly. So it's hard to think about it in terms of big O notation or a complexity class for that. The surrogate comparison is how many fundamental quantum gates do you need in order to build up the Fourier transform here? Because generally, with these quantum computers, what happens is that you each time that you are implementing a unitary gate, there needs to be some physical way that this is actually affecting particles. And so for these quantum computers, you're only implementing a few basic gates, which are incredibly expressive, in which you can use to build up more complex unitary transformations like the QFT. I believe that people have investigated this already, and they have a complexity class for how many unitary gates, how many of these fundamental unitary gates it will take to construct the QFT. So that's probably the best surrogate for the complexity of that. I believe, what was the second part of your question?
Was the dimensionality of the input X.
Yes.
So what I wanted to mention is that even though the Fourier transform or Poisson transform, they are applied for like one-dimensional, two-dimensional, three-dimensional signals, it is generalized to higher dimensions.
Yes.
And in that case, the transformation matrix is not unitary.
Yes.
So what I think is that it was nice that you mentioned the hybrid computation, for instance, for neural network. But so maybe there is some limitation in the presentation of the functions because you describe only using the unitary matrices, right?
Yeah. So
maybe are the transform matrices limited to unitary matrices and Hermitian matrices?
So they would be limited to unitary matrices. Yeah, you can have when you're taking these measurements and you are computing some expected values of the circuit, you can end up modeling functions that are not simply unitary transformations. However, in terms of what's actually happening in the real guts of the quantum circuit when we're modifying the qubit state, it can only be a unitary transformation. When we're measuring things, there's actually a surprising amount of expressive power that you can do. So, for example, like in this O et al. Paper, what they're trying to do is make the circuit act like a convolution, like a classical convolution. And so this isn't clearly a unitary transformation. So this is just an example of how with unitary transformations in the gates alongside some measurement, we can have a quantum circuit be more expressive than simply unitary transformations.
Other questions? Also online? Any questions online? Please raise your hand or just post the message in the chat. Right, doesn't seem to be the case. Then this concludes today's presentation, and let's thank Cameron once again. Thank you.